All right, welcome to the problem solving video for 2.5 Lewis structures. Sorry I didn't have this posted earlier. I had a very busy Wednesday, Thursday after school, so we're probably watching this during class. So let's go ahead and get into it. So we're going to look at some examples of how to write Lewis structures, okay? And the way that I've taught this in the past is not quite like this, but we're going to use this method for now until we get really comfortable with how to write Lewis structures. Okay, so this is a very methodical, step-by-step process that you can follow, which I know a lot of you guys like, so hopefully this is not too bad. So there's three big steps. The first thing you're going to do is you're going to figure out what is the total number of valence electrons from all the atoms that are participating in the molecule. Okay, don't worry about keeping track of which electrons come from which atoms. That will matter at some point, but for right now, it's just the total number of electrons that is important. Okay? What you're going to do then is you're going to use a pair of electrons to form a bond between each pair of bound atoms, and you're going to arrange the following electrons to satisfy the duet rule for hydrogen and the octet rule for the other elements. Now, really, you're never going to have to add extra electrons to hydrogen because, right, hydrogen follows the duet rule. So as long as hydrogen is bonded to another atom using a pair of electrons, it should never have any extra electrons. There shouldn't be any lone pairs on hydrogen. But there probably will be for other elements. Okay, so we're going to look at a couple of example problems. These both come from Chapter 8. We're going to look at number 85, one of my favorites, methane, CH4. And then we're going to look at a trickier one. This is also in Chapter 8, part of question number 88. This is the hyperchlorate, or I want to be careful about this, hyperchlorate ion, okay? This is a polyatomic ion. This is ClO4 with a -1 charge. So we're going to look at how we could write the Lewis structure for this. So this one's going to be a bit more complicated than methane. Okay, so let's go ahead and get into it here. All right, so this was for number 85, part D, CH4. Okay, so step one, we should, and I'll actually write the steps out over here. Step one, we should sum the total of valence electrons present in all of the atoms here. Okay, so here's my periodic table. Carbon is in this column here. Carbon has 4 valence electrons, along with silicon, germanium, tin, lead, etc. Okay, so these have 4 valence electrons. So carbon has 4, and there's 1 carbon, okay? And I have 4 hydrogens. Hydrogen is over here in the first column. These elements all have 1 valence electron, okay? So each hydrogen has 1 valence electron. So I've got 4 times 1 there. This is a total of 8, okay? So I have 8 total valence electrons. Step 2 was to bond each pair of atoms with a sharing pair or a bonded pair of electrons. You have to draw the arrangement here, okay? So, and there's actually 2 different ways to do Lewis structures. So carbon is going to be your central atom. I think they even give that to you as a hint in the problem in the book, okay? And you can do this in a couple of different ways. The way that I'm more familiar with and the way that I prefer is to draw bonded pairs as lines, okay? Each line represents 2 electrons, okay? It's a bonded pair. So that actually uses up all of my electrons, okay? So remember, step 2 is to draw bonded pairs. You're essentially wanting to connect each atom to some other atom. All the atoms should be connected together to form the one molecular structure. Okay, you don't want to have any atoms that are just hanging out by themselves. Everything needs to be connected into the molecule. Step 3 is to ensure that the octet rule, sorry, phone's going off, is to ensure that the octet rule and the duet rule are being followed. Okay? So let's actually look at the duet rule first. Each hydrogen should have 2 electrons. Well, each hydrogen has a bonding pair. Okay, So this hydrogen has 2, this hydrogen has 2, so on and so forth. All right, so our duet rule is satisfied. The octet rule is going to apply to all elements other than hydrogen. So carbon is the only atom here other than hydrogen. Carbon has 4 bonded pairs. Each of those lines represents 2 electrons that are shared, so that's a total of 8. Okay, so our octet rule is being followed. We're good to go, all right? Now the other way that you can draw this, and sometimes you will see it drawn like this, is like this, okay? So it's still the same configuration here, except instead of lines, sometimes people will draw the actual dots, so like the actual electrons like that, and actually, let me draw that a little better. Sometimes they'll draw it real close together, like this. I'm not a big fan of this method, okay, but sometimes you might see that, all right? These two right here are functionally equivalent to each other, okay? So those mean the same thing, all right? It's just sometimes you might see it drawn like this in various places, okay? I prefer to use the lines, though, okay? All right, let's go on to the next problem. This is number 88, part A. And once again, this is the hyperchlorate ion. So it's ClO4 with a -1 charge. Okay, let's add up the valence electrons. Okay, so this is step 1, right? So chlorine has 7, okay? Each oxygen has 6, okay? And this particular polyatomic ion has a -1 charge. I have 1 extra electron, okay? That's how that works, all right? So if you're working with a polyatomic ion or some sort of charged system that has an overall charge, you can factor that in here, okay? With an extra electron there. Okay, if this had -3, then I'd have 3 extra electrons. All right, so what's my total? Let's see, this is 24 plus 8, so what is that, 32? All right, so I have 32 total electrons. I think that's right, hopefully. All right, so once again, step 2 is to draw the bonded pairs. So let's see, chlorine is probably going to be my central atom here, since I have 4 oxygens. Okay, so I need to have at least 1 bonded pair. Okay, so let's see, between each oxygen and chlorine. Okay, that accounts for 8 of my electrons, 8 of my 32. And if you notice here, that's actually going to satisfy the octet rule for chlorine, okay, because it's 2, 2, 2, and 2. Kind of like the situation with carbon up there and methane. So I don't really need any extra electrons on chlorine, right? So that's what we're doing now is step 3, right? We're trying to verify that each atom follows the octet rule. I shouldn't put a check there yet. Okay, so chlorine is good, but what about the oxygens? Well, each oxygen only has 2 electrons right now. Should have 8. So we started with 32 electrons. We've used 8 here. So now we're at 24, okay? Turns out that each oxygen here needs 6 more electrons, right? They have 2, so they need 6 more to get to 8. And if I divide my 24 divided by 4 oxygens, each oxygen is going to get 6 electrons. So that means each oxygen should get 3 lone pairs. That was a bit of a convoluted way of saying we just need to spread out the rest of these electrons on the oxygens. Okay, so the total number of electrons present here is 32, right? It's 2, 4, 6 on each oxygen, so that's 24, plus 2, 4, 6, 8, right? And that gets me to my total of 32. And everything here has 8 valence electrons, right? They're all following the octet rule, okay? Turns out that this structure here has an overall -1 charge, okay? And so this is a polyatomic ion that engages in ionic bonding with cations, positively charged ions, okay? All right, so hopefully that was a little bit of a decent example there. I know that if you were in my class last year, you've definitely seen examples like this, but we did not do any of these charged examples, and so that may be a little bit new for you. Okay? All right, thanks for watching, and like I said, we're watching this during class, I believe, so I'll see you right after the video.